Hello and welcome to my Physics Online short video lectures. In today's short video, I'm wanting to review a few key topics from Physics 1 that you'll want in Physics 2. Now this is not going to be an extensive review. I am trying to keep these relatively short, and it's assumed that you've already taken Physics 1 prior to taking a Physics 2 course. And you did learn quite a few things in Physics 1, everything from kinematics to forces to energy to rotational motion, dynamics, fluids, perhaps heat, maybe oscillators, energy, work, power, momentum, angular momentum, elasticity, equilibria, torques, etc. Not to mention vectors and scalars and a few other odds and ends. I am not going to review all of that in this video. However, if any of those terms are completely unfamiliar to you, you may want to revisit those sections from your Physics 1 notes. Physics 2 does build on Physics 1 in quite a few ways, and so that's part of why I'm doing this little review. But I'm going to focus on a few of what I would consider to be very key topics from Physics 1 that I kind of expect to see a few times in Physics 2. So some major things that I would expect you to see again and again are forces and what they do. It's kind of assumed you already know how that is. We'll be discovering some new types of forces and how to calculate them, but you still are expected to know how forces interact with systems, etc. The other major topic that you're going to want to review from Physics 1 is work and energy, and specifically the work and kinetic energy theorem, and then the relationship between work and potential energy. So I think that those two topics are maybe the two most important to build onto in physics, from Physics 1 into Physics 2. And Newton's third law also is kind of important here as well, although you can always get the results from it via other ways. Okay, so let's start with the forces part, and I'll throw in Newton's third law. So forces, you'll recall, a force is a push or pull. What it does is it changes an object's momentum. And if it is just simply a force, it changes an object's linear momentum, and if it is acting as a torque, so as a torque, it changes the object's angular momentum. Now, as a torque, we will leave off today for the purposes of this review. The relevant equation in Newton's second law, to some extent Newton's third law. Newton's first law, by the way, is the equilibrium condition. Basically, there are two conditions for equilibrium. The first is that the sum of forces on an object is zero. The second is that the sum of torques on the object is zero. Okay, but the main equation that we need today for our review is Newton's second law, and maybe the third law to a lesser extent. Newton's second law is the one that says that the sum of forces acting on an object is the rate change of the object's linear momentum, which is often rendered for constant mass. So if mass is constant, it's very commonly rendered as sum of forces is mass times acceleration. Okay, So that's a very important thing to remember. Force changes linear momentum. Force usually causes acceleration. In this semester, we will have some mechanical forces, but also some electromagnetic forces. Basically, we assume that you already know force. We assume that you already know Newton's second law. And the new thing that happens here is that we just have new ways of getting force. For example, you'll be introduced to Coulomb's law, which governs forces between charges. You'll be introduced to electric fields and Gauss's law, which also ties into forces between charges. You will learn about how magnetic fields interact with moving charges and how that force works. You'll also learn a little bit about forces from Hooke's law, which you may have also seen in Physics 1. Okay, so that's sort of the first big thing. Newton's third law, for what it's worth, also important. Newton's third law. Every action force has an opposite direction and equal magnitude reaction force. There weren't a whole lot of great examples for that in Physics 1. Frankly, some of the best examples come in Physics 2. But, oops, I've kind of miswritten this a little bit. Usually we write this as force of object 1 on object 2 is negative of force of object 2 on object 1. And remember that force is a vector, hence the little vector symbol above it. In Physics 1, most of the examples probably felt contrived, at least until you got to Newton's law of universal gravitation, in which case you could actually calculate how much force, say, the sun applies to the Earth, and then how much force the Earth applies to the sun, independently of Newton's third law, and obtain, well, the same result that Newton's third law predicts. We'll have a few more examples of that this semester. So Newton's third law is a very good double check, and it's a good way to answer some conceptual questions both in my class and for those of you who are going to take something like the MCAT or the OAT or some other standardized exam that has some physics in it. Sometimes it's easiest to get the answer via Newton's third law. So let's look at Newton's second law very briefly. Sum of forces is mass times acceleration, or its rate change of momentum. Usually it comes in this form. So we have an object sitting on an inclined plane. It's a frictionless plane. We're given the mass of the object, we're given the angle of the plane, we're asked to find the acceleration and maybe find all the forces. So we know, whoops, I want to switch colors here. We know that the sum of forces acting on the object is the mass of the object times its acceleration. This basically is another way of saying that the gravity force plus the normal force is the mass times the acceleration. Now, how did we get that? Well, another key point for forces and problems in general is draw a nice diagram. Could be a free body diagram, could be a simple force diagram. So in this case, our diagram basically ends up having for us two forces. Whoops, the second force is maybe a little overkill. Two forces. We have a normal force between the ramp and the object. We have a gravitational force, which is just m times g. You know that this normal force from Physics 1 is m times g times cosine theta, and you know that they're in different directions. So how do you resolve the directions? Well, you go and do vector addition either by breaking stuff up into Cartesian coordinates or by doing tip-to-tail addition. The tip-to-tail addition version, for what it's worth, you would end up with your object like this, and so here's your normal force, comes to here, and then here's my ramp. Gravity comes down to here, so here's gravity, here's the normal force, and so this right here would represent the sum of forces. And in Physics 1 we just said let's define this direction along the ramp to be the x direction, and it turns out that if these two right here make a right angle, and so if this angle right here is theta, then this one goes with cosine and this one goes with sine of theta, and so what you end up getting is m times g times sine of theta is m times a, and therefore a is g sine theta, or in other words 9.8 meters per second squared times the sine of 7.5 degrees. And so then we enter all of this stuff into our calculator. We have 9.8 times the sine, make sure you're in degree mode, of 7.5. You end up with 1.279, which to two significant figures ends up looking like 1.3 meters per second squared. We've solved the problem. All right, the second thing that we want to review is the concept of energy, and energy is basically how much work it takes to do or to get a system to a certain state, or how much work a system can do. So energy and work. So first of all, we have the work and kinetic energy theorem. So work and kinetic energy theorem. And that one basically says that the net or total amount of work done on a system is the change in the system's kinetic energy. So this is total work. Really, it's usually for an object, on object. And that could be a negative or a positive number, by the way. And this is kinetic energy, or delta, change in. So change in, and K is kinetic energy. Now recall that kinetic energy, for what it's worth, is 1/2 mv squared for an object that is translating, and 1/2 I omega squared for an object that's rotating. Usually we focus on this part of it, but if you have rotational motion, then this other part also is important. Okay, the second thing that was with work and energy was potential energy and work. And potential energy, U, we usually use a capital U, is the potential of a force in a system to do work on an object, or really on a pair of objects. So on an object in the system. Only valid for conservative forces. And so conservative forces are basically forces that conserve energy within a system. So gravity and Hooke's law force, basically any of the field forces, electromagnetism, any of that. Now the key take home from this second one, and this is maybe the most important of Physics 1 energy stuff that goes into Physics 2, key take home is that this means that within a system, the work done within the system is equal to the opposite of the change in the kinetic energy. Or in other words, and this is energy conservation, change in kinetic energy and change in potential energy are equal. Sorry, I said work done is the negative of the kinetic energy. I meant to say that the work done is the negative of the potential energy change in the system. So W equals negative U, but that ends up being delta K within a system as well. And this is for, this would be total, this would be total, and this would be total. But for an individual conservative force, so we'll just say it, individual conserving force, that would be the change in potential energy associated with that individual conserving force. Okay, and that's very important because it gives us a method, when combined with this third thing, of figuring out potential energies for a system. Because the third thing is how to define work. And the assumption here is that you have a constant force. That basically just means that the force has the same magnitude at all times, and it's always in the same direction as the instantaneous displacement. So the way that work then was defined for a given force, triple bar means defined as, it's the force dotted with the displacement. And what that looks like is either F times D times cosine theta, or in vector form, this is Fx times delta x plus Fy times delta y plus Fz times delta z. And the diagram that usually goes with this, for what it's worth, is that you have some object that's being worked on. So for example, maybe I have like this really heavy crate, and I'm going to pull on the heavy crate against the ground. So I've attached like a rope to the heavy crate, and I'm pulling like this, and the result is that the heavy crate is going to move across some distance. So this right here would be my displacement vector. This right here would represent the magnitude of that vector. This angle between them is angle theta from this equation. So this is the force, this is the displacement, this is the angle theta. And that's how you find how much work is being done. But that also means that this is how you find how much potential energy a given force within the system can have, because it's this is not an example of a force that conserves energy, because I'm adding energy to the box by pulling on it. But if I have, say, gravity, and I have an object that's going to fall, so it's on the ledge, it can fall up to some height h, then the total work that this could potentially do is the force, that's m times g, times the maximum distance it can fall before, well, not being able to fall further. And ostensibly the object's going to hit the ground and then not fall further. It could fall farther. It could break, it could be a table that it breaks through. It could also be stopped short. Somebody could come over here and catch the ball here. So maybe I've got a person standing here ready to catch the ball when it falls, in which case it only falls some shorter distance. Okay, so if that's true, then the work would have been mg times delta y. But the potential energy would have been mgh. Okay? So I guess this is the last point in this, and then maybe I'll do a brief example. Last point. To get work or potential energy for force in general, plot force versus position or displacement. So force versus position, and then area under curve equals potential energy, or work. And the reason why there's an or is this. Let's say that I've got some particular force here, and I've got some particular position here. And let's say that the force does, something like this. And let's say that I have picked this right here to be my initial position. Well, this right here, whoops, I drew my line a little backwards here. This right here, this whole area, actually before I do this, let me copy this because I'm going to duplicate it in a minute. This whole area is going to give me the potential energy. So this right here is my potential energy. Now, if I want to figure out how much work is actually being done by this system, this is why I've made a copy of it. If I want to figure out how much work is done on the system in moving from one point to another, maybe this is my x final, then this area right here, and let's do it actually in green for variety, this area right here would represent my work. It also represent my change in potential energy. So the work done by this force is a positive amount. The change in potential energy is a negative amount because this right here, whoops, would represent my final potential energy. This is my initial potential energy. And so notice that the work done is positive, but my change in potential energy is negative because I ended with less than I started with. Okay, and this works for a force that is not constant. It also works for a force that's constant. Okay. Maybe one example. All right, so I've got this little diagram of a box going along a ramp. It doesn't matter if it's frictionless or not, but let's let it be frictionless. And I have a start position and an end position, and there's really two things that we could ask here. What is the initial and the final gravitational potential relative to the bottom of the ramp? So what is the gravitational potential energy relative to bottom of ramp? And notice we always have to say relative to some point. You get to pick where that point is, but for convenience, bottom of the ramp is often it for these ramp problems. And the other thing is how much work will gravity have done? to the box from start to end. Okay, so to get gravitational potential energy, U should look like m times g times h. And so this right here would be my initial height. This right here would be my final height, h final. And basically, I can see that the height is sort of across from the angle in a right triangle, because this is always going to be a right angle. Height versus horizontal is a right angle. And so this angle right here is my 8.8 degrees. So height, if this is the x direction, height is x times the sine of the angle. Okay, so height initial would be x initial sine theta. And so that means that my initial height, 2.4 plus 1.2 is 3.6 meters, times the sine of angle 8.8 degrees. So going with my calculator, oops, I have 3.6 times sine of 8.8. Okay, and that is 0.5507. I'm going to retain some extra digits and round at the end, but we could say 0.5507 meters to sig fig. Okay, and the final height, h final, likewise is x final times sine of theta, ends up being 1.2 times sine of 8.8, or in other words, a third of this number. So 0.1835 meters, again 2 sig figs. All right, so that means that U initial mgh, that'd be mgh initial, is equal to 15 kilograms times 9.8 meters per second squared, which is the same as 9.8 newtons per kilogram, times 0.5507. So enter all that into the calculator, and we get 80.96. Remember that the unit is joules. Rounding to 2 sig figs, this is about 81 joules at 2 significant figures. If we do the same thing for the final, we'd have mgh final. All right, so that's 15 kilograms times 9.8 meters per second squared, or 9.8 newtons per kilogram, times 0.1835 meters. And that gives you 26.98. So 26.98 joules. 2 significant figures per this. So U final is about 27 joules. Okay, now we got to calculate the work. Work should be force times distance times sine of the angle between the force and the distance. All right, well, the force is vertical, the distance is in, sorry, times the, I said sine, I meant times the cosine, excuse me. Force times distance times cosine of the angle between the two. And I've already labeled theta in this problem as the angle of the ramp, so I'm going to have to use phi as the angle between force and displacement. So if I were to draw the force up here as a green arrow pointing in the direction of the force, this would be the force vector, and so this right here is angle phi. But notice that angle phi and angle theta are opposite angles on a right triangle, so we know that this is the same as F times delta x times sine of theta. Remember that opposite angles on a right triangle means that the cosine of one is the sine of the other. So the work done is force, which is m times g, times delta x times sine of theta. So putting all this in, my force, m times g, is 15 kilograms times 9.8 newtons per kilogram, times delta x, which up here is 2.4 meters, times sine of the angle, which is 8.8 degrees. You could also use the cosine of the angle phi, which is 81.2, if you prefer that. So let's put all that in. We got 15 times 9.8 times 2.4 times sine of 8.8, or cosine of 81.2. We get 53.97 joules, but this should be at two significant figures, so the work done is 54 joules. Now, as a double check, you'll recall from the previous that we said that work should be negative of delta U. So if I take this number and subtract it from this number and then take the negative, or in other words, if I subtract this final from the initial, then I should get the work done. Well, 81 minus 27 is in fact 54. So we could have done work equals negative of 27 joules minus 81 joules, which is 54 joules, and gotten the same answer. Okay, now this video has already made it to well over the 30-minute mark. I'm trying to keep these short. This one is by necessity long because I'm reviewing a lot of things from Physics 1. But I hope you got a lot out of it, and hopefully this brings you up to speed, along with maybe a few other supplemental videos, up to speed with where we're going in Physics 2. So thanks for watching, and let's have a great semester.